In this video, we are going to discuss about RL series, RC series and RLC series circuits. Okay, so what is that circuit is? In previous video, we discussed only the single element across the supply, single phase supply, how it performs, whether it stores or whether it consumes the energy. So in that pure resistor, the resistor consumes power, and if L and C, then it stores the energy and it releases the energy. So that we discussed in the previous slide. So now if it is a combination of RL or RC and RLC, then what's the performance of the series circuit across the single phase supply? So there are three series circuits: RL, RC and RLC. So we'll discuss one by one. So now first is about RL series circuits. So what is an RL series circuit? So series combination. Resistor and inductance are connected in series across single voltage source. Voltage source V can be written as Vm sin omega t. And the current is I. And since there are two elements and which is connected in series, we can say voltage across the elements, the resistor and inductance are different. So normally in series circuit, in series combination, voltages are different, but current comes same. Means the current across the resistor and the inductor is same, but voltage across the resistor and inductors are different. So here RL both are connected in series. So VR is a voltage across the resistor and VL is a voltage across the inductance, and the current I which flows same through the resistor and as well as inductance. And V equal to Vm sin omega t, as it is, we are considering it as a first equation. It's a mathematical representation of the applied voltage. And since there are two voltage drops, one is across the resistance and one more is across the inductance, we are writing it as a VR equal to, according to the Ohm's law, it's I into R, and VL, it's I into XL. I is the current through the inductance and XL is the inductive reactance, and XL can be written as 2 pi FL, and the unit of inductive reactance and capacitive reactance are same only. The same thing, but the resistance of resistance opposes the current in the resistor circuit, and even the reactance opposes the current in the inductance and the capacitor circuits. So now it's about the phasor diagram. And to know the phasor diagram for this series combination RL, so first we have to analyze the phasor diagram of resistor and phasor diagram of the inductance. So we know in a resistor circuit, voltages and current are in phase. In the resistor circuit, voltage and current are in phase, but in an inductance circuit, the current lags the voltage by 90 degree. Current lags voltage by 90 degree in the inductance. So what is a combination? The resistor and inductance combination gives this as a phasor diagram. So we are considering the current as a reference here, because in a series the current is same across the resistor and inductor. So we are considering the reference as current. And as we know, in resistor, voltages and current are in phase. So VR is the voltage across the resistor that I am considering in this reference itself. And next VL. Since we are taking I as a reference, so we can invert it, or we can rotate this phasor diagram of the inductance. So if you take I as a reference, so what happens is the VL comes in the this direction. So we are taking I as a reference. So if you turn it, then the voltage across the inductance, that voltage goes up. So this is a voltage across the resistor which is in phase with current, and this is the voltage across the inductor which is having the phase difference of 90 degree. So we are considering I as a reference, since it is a series circuit. The current is same across the resistor and inductance. So voltage and current are in phase in the resistor, but current lags voltage by 90 degree in the inductor circuit. So if you take normally this is a phasor diagram of the inductance, no? So if you take I as a reference, then the VL comes above. This is a VL, this is VL, and this is VR. So combining these two voltages gives a total voltage V. So total voltage V. So this is VL. So we can consider this also as a VL. So VL. And this is VR. So this gives you one triangle here. So what is the phase difference? The phase difference here is 90 degree. And what is the phase here? Phase difference is, we are considering it as a phi. We are considering it as a phi. Means the current lags voltage by angles phi. So we get a triangle over here. It's a voltage triangle, means this part. This is a voltage triangle where all the three sides are voltages. This is the total voltage V by considering VL and VR. So VR is equal to IR and VL equal to IXL, which gives the total voltage V in this RL series combination. So if you write a KVL equation for this, then we get V minus VR minus VL equal to 0 and V equal to VR plus VL, and VR we are substituting as I, R and IXL. And since it is a triangle, right angle triangle, we can use a Pythagoras theorem. So OB, this OB adjacent, this diagonal OB equal to square root of OA, this side OA the whole square plus AB the whole square. So when you substitute, we get V equal to I square root of R square plus XL square. Or we can say I equal to V divided by Z. I equal to V divided by Z. So what is that Z? Z is an impedance. Since it's a combination of resistor and inductance, we consider it's as a Z. Not a resistor, not an inductor. It's a combination of resistor and inductance. So Z is the combination of resistor and reactance. So Z equal to, we can write it as square root of R square plus XL square. So V equal to Vm sin omega t. It's the applied voltage across the RL circuit. And what about the current I? As per this phasor diagram, current lags this voltage. Current lags the voltage by phi. So I equal to, we can write it as Im sin omega t minus phi. So in a resistor, both are in phase, but in inductor, it's lags. But here it is not by 90 degree, it's by some angle phi. So phi value lies between 0 and pi by 2. So this phi value lies between 0 and minimum 0, maximum is 90 degree. And even we have one more triangle called the impedance triangle. If you represent all the sides in terms of impedance, then it is an impedance triangle. So R, this lower side, this is for resistor. So R equal to, we can write it as VR by I. And in the this side, it's VL. VL equal to IXL according to the voltage triangle. So I equal to what? VL divide, XL equal to VL divided by I. And this side, which is for total voltage V. So Z equal to V divided by I according to this equation. Z equal to V by I. So all the sides we are representing in terms of impedance, because impedance is Z equal to the combination of R and XL. So it's called as a impedance triangle. And next is about the waveform, voltage current waveform. So we know V equal to Vm sin omega t, V equal to Vm sin omega t, and I equal to Im sin omega t minus phi it is. Current lags voltage by some angle phi. It's not pi by 2. So we are considering the voltage where it starts from 0 and pi and 2 pi, and current lags the voltage by some angle phi. So don't consider it as a pi by 2, because the value of phi lies between 0 and pi by 2. So somewhere in between 0 to pi by 2, start one waveform and represent it as a current waveform. So over the instant, it will maintain some phase difference of phi. And phasor diagram, so voltage, and previously it is in pure inductance circuit, current lags voltage by pi by 2. Here it is phi. So it's not a right angle triangle. So voltage and make some phase difference of phi here. So current lags voltage by some angle phi. So this is a phasor diagram of RL series combination. And next is about the power. So resistor consumes power and inductance stores and releases the power in a magnetic field. So we'll see what is a power for the series combination of R and L. So as usual, we are starting with the power equation, general equation, P equal to V into I. So we know what is V, which is Vm sin omega t, and I is Im sin omega t minus phi. So multiplying it, and we have to simplify to get the average power. So for that, we are considering one formula, trigonometric formula, sin A sin B, which is 1 by 2 cos A minus B minus cos A plus B. So according to that, A is omega t and B is omega t minus phi. So A minus B gives you phi here, and A plus B gives 2 omega t minus phi. So we'll see the average power. So average power is by considering one full cycle, which is 0 to 2 pi. So 1 by 2 pi, 0 to 2 pi, P into d omega t. So 1 divided by 2 pi, what is it P according to the previous equation, which is Vm Im by 2 cos phi minus cos 2 omega t minus phi d into omega t. So here integration with respect to omega t, so rest all will be the constant. So Vm Im divided by 2 goes outside, which will be 4 pi, and 0 to 2 pi cos phi and minus cos of 2 omega t minus phi into d omega t. So consider the integration for both the terms. So it will be like integration of cos phi d omega t and integration of cos 2 omega t minus phi d omega t, and integration with respect to omega t, and there is no omega t term in this first term. So it cos phi remains constant. So d omega t, integration of d omega t is omega t. Integration of d omega t is omega t. And what about the second term? There is a omega t in this. So integration of cos 2 omega t minus phi with respect to omega t is sin 2 omega t minus phi divided by 2. 2, there is a constant over here, so divided by 2, 0 to 2 pi. And anyhow this term will be 0 because sin n pi is 0. Sin pi n pi will be 0. So we are considering the cos term, cos phi omega t, cos phi omega t. In the place of omega t, we are going to substitute the limits. So cos phi 2 pi and cos phi 0. So cos phi 2 phi and cos phi 0 will be 0. So cos phi 2 phi, and here when you simplify, you will get Vm Im divided by 2 cos phi. So as it is, root A into root A is A. So root 2 into root 2 is 2. Vm by root 2, Im by root 2, which is a VRMS value. So Vi and cos phi, which is a power factor. So average power for this series combination of R and L is not equal to 0, and it's not equal to Vi, it's Vi cos phi. So phi value ranges between 0 to pi by 2. So cos phi is nothing but power factor. So the value of cos power factor lies between 0 and 1, because cos 0 is 0, cos phi here. If it is pi by 2, then cos phi by 2. Cos 0 is 1 and cos pi by 2 is 0. So value of cos power factor lies between 0 and 1. And this is a power waveform for RL series combination. And here there is a phase difference of phi between voltage and I. So the negative cycle, that will be very small compared to the positive half cycle, because the phase difference is very small, it's not pi by 2. So when you draw the waveform in the negative half cycle, we have to maintain a small amplitude. And as it is, if it is plus and plus, then the value is plus. Plus and minus, then it is minus. Minus and plus, then minus. Minus and minus will be plus. So we get a waveform in this way. And what this says is, A to B, this instant, the first instant, A to B, the inductor returns power to supply. Negative half cycle represents returning power, and positive half cycle is consuming power. So B to C, resistor consumes power, and again C to D, inductor returns power. So that's about the RL series combination. And next, RC series combination. In the same way, we are considering a circuit where R and C are connected in series across the single phase supply. So R and C are connected in series, so voltage across resistor and voltage across the capacitors are different, but the current through resistor and capacitor comes same. So we are writing voltage across the resistor as I into R as per the Ohm's law, where voltage and current are in phase. And capacitor, where voltage across the capacitor is represented as Vc, which is I into Xc, and I leads a V by pi by 2. If you consider it pure resistor and pure capacitor. And yeah, just to analyze the phasor diagram of this combination, RC combination, we'll consider it separately, one for a pure resistor and one for pure capacitor. So we know in a pure resistor, voltages and current are in phase. In pure capacitor, the current leads voltage by pi by 2. Current leads voltage by pi by 2. So this is a phasor diagram for R and C. So current leads voltage by pi by 2. So what is a phasor diagram for this combination? So for this we are considering I as a reference, because for a series circuit, current through the resistor and current through the capacitors are same. So we are considering I as a reference over here. So voltage across a resistor we are considering in this reference itself. And what about the capacitor? So if you take reference as I, then voltage that comes down, which is VC. So even this side will be VC and this side will be VR. So this gives you a resultant vector, which is a total voltage V. So total voltage V makes some angle phi, and this total voltage which makes angle pi by 2. Right? So the voltage, this voltage and this current makes some angle phi. So as per the previous consideration, V equal to, since it's a voltage triangle, V equal to, we can write it as VR square plus VC square. V is IR, so IR the whole square plus VC is IXC the whole square. And if you simplify, you will get I equal to V divided by root of R squared plus XC squared. So this root of R squared plus XC squared is nothing but the impedance of the circuit. So impedance is a combination of resistance and reactance. So Z equal to root of R squared plus XC squared. So we can represent the same by using the impedance triangle too. So what about V? V is Vm sin omega t according to the first equation. And what about I? So if you consider a resistor, both I and V are in phase. But if you consider a capacitor, current leads voltage by some angle phi by 2. But here it leads the voltage by some angle phi. So I equation comes as Im sin omega t plus phi. So waveform for this RC series combinations is the current leads voltage by some angle phi. So we have to show some difference of phi. It's not pi by 2. We have to show the value which is in between 0 and minus pi by 2. So this is a leading of current compared to the voltage, and this is what the waveform of voltage current waveform of RC's combination. The next phasor diagram. So voltage and current, and the phase difference is phi. It's not pi by 2. In a combination, the difference is phi. So remember, if it is minus phi, then it is lagging. Plus phi is for leading the voltages. And next, power, as it is P equal to VI we consider, and Vm sin omega t and Im sin omega t plus phi. And here for simplification we are using sin A sin B formula, and cos of minus phi we get cos of minus theta is cos theta, and this term we have written as it is. And next, finding what is the average power. So PAV equal to 1 divided by 2 pi 0 to 2 pi P of d omega t. So integration, remember, it is with respect to omega t. So phi remains constant here, which lies between 0 to pi by 2. So 1 divided by 2 pi 0 to 2 pi Vm Im by 2, and we are substituting this word here. Its entire term is substitution with respect to d omega t. So Vm Im by 2 remains constant, so we are taking it out, and here cos phi is constant, so integration only with respect to omega t, and here the integration of the entire term. So when you integrate the cos to omega t plus phi, it gives sine, but whatever the value of limit term, you will get 0. So we are neglecting the second term. So Vm Im divided by 4 pi cos phi d omega t, integration of d omega t is omega t, and upper limit is 2 omega t and lower limit is 0. So cos phi into 2 pi and cos phi into 0 is 0. Okay. So Vm Im, this gets cancelled. Vm Im divided by 2 cos phi. And 2 can be written as in terms of RMS, it's root 2 into root 2. Vm by root 2, Im by root 2, which is Vrms and IRMS. We can write it as Vi cos phi or Vrms IRMS cos phi. So this is the average power for the RC combination. And this is a power waveform like the previous one. Since the phase difference is very small within angle 0 to pi by 2, the cycles are not exactly same. Positive half cycle which maintains a maximum amplitude compared to the negative half cycle. So that's what here the amplitude we are maintaining, whatever it is, we are maintaining it as a less, because the phase difference is just a phi. Here the phase difference is more and here it is very less. Okay, so the phase power waveform for RC combination is this one. Next, RLC series circuit. So RLC series circuit is a combination of resistor, inductor and capacitance across the single phase voltage supply V equal to Vm sin omega t. So we have three voltage drops. One is VR and YL and VC. So current comes same for RLC, voltages are different. So voltage across the resistor is IR, voltage across the inductor is IXL and voltage across the capacitor is IXC. So in a resistor, voltage and current both are in phase. In inductor, current lags voltage by pi by 2 and in capacitor, current leads voltage by pi by 2. So if you apply KVL for this closed circuit, we get V equal to square root V equal to VR plus VL plus VC, or we can say it as V equal to square root of VR square plus VL square plus VC square. Since there are three combinations and one consumes power and two stores and releases power, we are considering three different cases. One is RL and second one is RC and third one is pure R circuit. Means the same combinations of circuit. What happens when it behaves like RL, RC and pure R? So we are having three cases over here. One is if XL inductive reactance if it is greater than XC. If inductive reactance is greater than XC, obviously voltage across the inductance is greater than capacitance, right? Because we have one consumption and two storing. So we are checking the priority over here. So if XL is greater than XC, then VL greater than VC and the entire circuit acts as a RL circuit. If XL is less than XC, in a sense XC is greater than XL, so VL is less than VC, means VC dominates over VL. So the circuit acts as a RC circuits. And if XL and XC both are same, then voltage across the inductance and capacitance comes same and it cancels over and the circuit, the RLC circuit acts as a pure R circuit. So we'll see all the three cases with just a phasor diagram. And first case, inductance is greater than capacitance, VL greater than VC. So we have equation over here which is V equal to square root of VR square plus VL square plus VC square. So now what happens? VL is greater than VC. So we can write the equation. Same equation is VR the whole square plus VL minus VC the whole square. Substituting what is VR, VL and VC, and when you simplify, we get V equal to I square root of R square plus XL minus XC the whole square. So what is this? It's nothing but the impedance. So impedance is a combination of resistance and reactance. The circuit is similar to the RL circuit, means it behaves as a RL circuit if XL is greater than XC. And so V equal to Vm sin omega t anyhow, I equal to Im sin omega t minus phi because the inductor lags. And average power in a RL combination we got a Vi cos phi, and even the phasor diagram will be same. What about this one? So phasor diagram of RL. So here what we are doing here is just writing it as VL minus VC because we are considering the circuit RLC circuit by considering three different cases. What happens if XL is greater than XC and XC is greater than XL and XL and XC come same? So writing VL minus VC is very important. And here we are writing it as VL minus VC, and even here it is a VL minus VC, and the phase angle which is phi between voltage and current, rest all are same, just writing VL minus VC is the difference over here. And next, second case is XL, which is less than XC. In a sense, capacitor dominates over the XL inductor. So XL is less than XC, therefore VL is less than VC. So we are writing the total voltage V as root of VR the whole square plus VC minus VL the whole square. Substituting, and we are getting it as a I equal to V divided by square root of R square plus XC minus XL the whole square. So this denominator term represents the impedances. So V equal to Vm sin omega t, and it's a combination with capacitor, right? So capacitor leads means the current leads voltage in the capacitor, so it's plus, so plus some angle phi. So I equal to Im sin omega t plus phi, and the average power, as we know, it's Vi cos phi, and even the phasor diagram is same, vector diagrams are same. So just we have to mention it as Vc minus VL or VL minus Vc. So in the first case, the RLC circuit, it acts as a RL. In second case, RLC circuit acts as a RC circuit. And third case, if XL and XC both are same, then VL equal to VC. And what happens is it cancels each other. The voltage across the inductor and capacitor cancels each other. So the circuit acts as a pure resistor circuit. So Z is nothing but R. Because XL and XC both will be same and it's 0. So Z we get it as a pure resistor circuit. So for resistor circuit, V equal to Vm sin omega t and I equal to Im sin omega t. The average power we get it as V into I. So phasor diagram where VL and VC component we have to write, but it doesn't make anything because VL cancels with the VC. So, and we get only the pure resistor circuits in this reference, which is VR. Thank you.